Good afternoon for those in Europe. Good morning for those in the US. My name is Francesc Lordan. I'm a researcher in the Barcelona Supercomputing Center, and welcome. And today I will be the host of this 10th session of the webinars organized by the Discover Us project. Today we have with us Manish Parashar. I think that he needs little introduction. Manish, I think he's a reference in distributed computing, and actually he's a professor at the University of Utah. He's also the head director of the NSF cyber infrastructure office, and today he will give us the talk Beyond HPC, envisioning a cyber infrastructure continuum for science. So Manish, welcome, and the floor is yours.
Thank you, Francesc. Thank you, Rosa, for inviting me to give this webinar today, and thank you all for attending. Just one clarification. I used to be director at NSF. That was a year back. I'm no longer director now. I direct the Scientific Computing and Imaging Institute at the University of Utah. And let me start by saying a little bit about the Institute. This has been around for about 30 years now, or over 30 years. It is looking at translational research at the intersection of science and computing and data. So we have faculty from many different departments coming together at the Institute. We work on different aspects such as visualization and imaging, scalable computing, data analytics, and being translational in nature, we spend a lot of, we do a lot of software development, system development that we then translate back to the community. Again, we have, a lot of different software packages that we've deployed over the years. And then more recently, we've been leading an effort on translational AI. And if I have some time, I will talk a little bit more about it. But the theme here is, how do you use AI to impact and address important problems for our region: environmental sustainability, air quality, water sustainability, mental health, teaching and learning, right? So how do you use AI to address these challenges, and in the process advance AI as well? And if I don't get to this, please feel free to reach out to me, and I'll be happy to talk more about that. So let's get down to this topic. And this is a talk, you may have heard parts of it in the past, because I've been working on this for some time. And the idea is that given that our computing ecosystem is evolving from siloed systems to more of a continuum that connects the edge, the networks, the cores together so they can be used collectively. And this is specifically a case for science, right? And so while we are talking about Internet of Things and a lot of these things happening across all aspects of computing, it is especially true for science. And that's because we have built these large instruments that are, at the edge, right? They are not simple sensors, but they are remote like these sensor networks, and they produce a large amount of data, and they are far away from compute, right? So we can think about the edge as made up of not only these Internet of Things, and smart devices, but also these large observatories and instruments and experimental facilities. And here are just a list of few, such as LHC and Vera Rubin and Square Kilometer Array and NEON. These are providing different data sources and provide tremendous amount of data that allows us to do very interesting thing. And then we can combine that with more traditional sensor networks and the Internet of Things, right? In the core, we're seeing smarter networks with higher bandwidth, but also additional capabilities for data processing, for data staging in the network, right? So you can think of smart NICs and data transfer nodes in the network that can do interesting things with data. And then at the core, we have a diversity of computational platform from large-scale HPC centers to clouds and then hybrid systems in between that provide tremendous amount of computing, right? So if you look at this whole thing together, you get a continuum which combines these. And if you can look at this as a continuum, we can think about new types of applications. We can think about applications that can really close the loop. They can acquire information using these networks in near real time, assimilate that information and analyze it either in situ at the edge or in the network or the core, right? Model it and then use it to understand phenomena, predict, manage, optimize. And once I make those decisions using these models, whether they are data driven, AI based, or whether they're more um, mathematical models, I can use them together to then actuate and control a system, optimize a system, correct it, respond to some certain events, right? So I can think about this as an end-to-end workflow that really combines this. And this is really enabled. We've always had these discrete pieces, right? We could acquire information, but to be able to do it in this closed loop is what the continuum is evolving. And this is very important for science as we try to understand phenomena and we try uh, to respond to it, right? And there are different type of applications one can think of, right? This is something that has been happening for some time now, which is this end-to-end experiment management. And we have seen many examples of this, right? I remember working on applications like this almost 20 years back, right? Where you have data and you can combine data collection, experimentation, um, uh, operations with modeling and simulation, right? So how do you combine them to in some sort of an end-to-end loop? Previously, this was harder to do because of the discrete and disconnected nature of these different aspects. But now with the continuum, you can think about a more closed loop where you can use the modeling to manage, optimize the experiment, and then use the experiment to advance the simulations and models, right? And this becomes very important when we have very um, um, expensive instrumentation. So the figure you're seeing here is a more recent project that I was working on as part of the US exascale computing project. And in this, what they are trying to do is to manage a plasma physics experiment in a tokamak, right, using model. And the specific in this specific example, they're trying to minimize or to prevent uh, disruptions happening in the tokamak, which can damage the walls of the tokamak, which is a very expensive activity. So you want to run your experiment and get the physics, but you want to be careful. And the moment you're detecting these disruption zones, you want to stop the application or the experiment, right? And so this is this closed loop we can do using these models. Another one we worked on was an instrumented oil field where we're using um, data from the oil wells and from the oil field to be able to manage the oil production process, right? To be able to manage injection rates, manage the placement of production or the operation of production wells so that you can increase productivity, but also make sure you're minimizing impacts of the process. Uh, just generalizing this, and this is something I know others have been working on for some time, but is the idea of digital twins, right? Where you have a physical system that you're managing or understanding, trying to understand, and you have a digital systems, and they are coupled together, right? And so the idea is how do I create this near real-time coupling between the physical system and the digital system, which could be represented using a variety of models, right? And so that requires this continuous information flow between these two systems in a closed loop. And you can see many, many examples of this, right? Here you're seeing a few examples too. One is digital Earth for the twin for the Earth system, and then you can think about using it to understand using a variety of sensors and instrumentation, and to understand and model, and then you try to close the loop so you can assess things like, fire weather or flooding risks or extreme weather patterns, right? So you can think of a lot of uses where if I had a digital model of the Earth, right, and that is fed in near real time from uh, data coming from satellites and Earth-based sensors uh, in a closed loop, that can be very, very useful, right? Another one in the figure on the right here is a digital twin for the human immune system. And when you're thinking about personalized care, these become very, very useful, where I can create a digital model of organs or subsystems in the human body that can use to better understand and personalize treatments, interventions for that individual. It can also allow us to detect certain aspects early in the human body, and you're seeing these used in many different scenarios, including surgery and other things, right? So there's a lot of work going on, and there are a variety of things. You can think of digital twins for many complex systems, right? Engines, airplanes, automobiles that can be used to be able to manage these things. There's a link on this slide, which is a recent report about a year back now from the National Academies for Science, Engineering, and Medicine here in the U.S., which really talks in a lot more detail about this digital twins and the research gaps. Another area, and I'll come back to this in a bit, is the idea of urgent computing, right? Which is really built on this potential of a continuum. And the idea there is to how can I use the continuum to respond to urgent events? Think about um, uh, extreme weather situations, right? There's an earthquake, there's a hurricane, there's a fire, there could be any extreme scenario, a pandemic, a cybersecurity attack, right? How do I detect it and respond to it in a meaningful way? Whether the response is mitigating or reducing the impact of the damage it does, uh, saving lives, developing logistics to evacuate people. So you can think of many things that can be done if I can detect and respond to it in a meaningful time. And the basic idea here is to use this continuum to be able to identify events and categorize them, and to be able to detect a possible impact early, develop a response using available computing and models that we have and this data, and then actuate, trigger appropriate action, whether it's human action or automated action. How do you close the loop, right? Again, the same idea of closing the loop, but here the difference is the urgency of it, right? There's a strict time and quality constraints in the response. So I have to do the best I can uh, with the data I can get within that time, and the computing and the resources I can get, right? So it's a little different from a more uh, typical digital twin time system where there is a dedicated resources set up to be able to do this continuous optimization. Here you're reacting to something which is an exception. You were not anticipating this extreme event, but it happened. How do I react to it? Right? And then what are the decisions I have to make, and how do I support that? Again, the continuum can really help here. So let me switch a little bit and talk about some of the work we are doing. Right, there are a lot of research challenges out here, right? But I wanted to focus in on some of the specific research efforts that our group has been doing for a couple of years now on trying to address these kind of challenges and working and enabling different applications, right? And so and then after that, towards the end, I'll talk more broadly about the type of research challenges that and open questions this leads to, right? So one thing that we have been thinking a lot about is how do you drive computations through data? What does this mean, right? So as I said before, a lot of this thing is triggered by the data that you're seeing, right? Especially if your urgent workflows, depending on what my data is telling me, I have to make a decision as to what computations I do, where I do them, how fast I do them, what are the time and quality constraints I have. A lot of that depends on what my data is telling me, right? So unlike traditional workflows, the nature, the composition, the execution of a workflow will depend on what the data is. So can I build simple abstractions that can uh, that can allow me to express these possible computation based on possible data behaviors that I might see. Um, Another aspect is, once I've defined the workflow, I have to aggregate resources that I can run it on. And given again, this is not in an urgent situation, I may not have dedicated resources. So I have to opportunistically aggregate resources that I want to run within those time constraints. And then the other aspect that I've been interested in is to manage the execution in this environment so that I keep on, given that this is a very dynamic environment, how do I make sure that I'm managing my time and other quality constraints, right? So is that how do I make sure that the quality of service overall is managed? So there are three pieces of work. I'll spend a slide talking about some of them. So let me go to those, right? So one work that I've been doing, and again, with Daniel, who's now at INRIA, is to see what is a good um, set of simple abstractions that can run in a diverse set of environments, including the edge and very lightweight devices that can allow me to trigger the right actions, right? So you need a simple if then else kind of an abstraction that allows me to trigger execution, right? So what is the programming support to be able to do this in a distributed, decentralized environment? And then what is the underlying infrastructure that's needed to support it, right? And so the abstraction we have built is a simple one. It is codified into this our pulsar system that we built, and now we're actually integrating it into a production environment. And I'll talk a little bit about that. But the basic idea is that close to sensors on platforms at the edge, we can deploy this. And the idea is, again, a simple one of being able to detect patterns, right? So you could define filters or patterns based on individual data values and simple logical operations on these, right? But you can also define um, filters based on windows of data, right? Especially when you're streaming data, you could be defining operations. And here you could define them on behaviors over that window. For example, what is the average value in this window, right? Or what is the rate of change of information in this window, right? And so that allows me to do things like if I see that the rate of change is greater than something, then I'm interested in it. I can also do this across spatial windows across multiple sensors, right? So it allows me to have an abstraction where I can express things not just on individual sensor data values, but across windows of data in space and time, and based on the statistical first order, second order, or a higher order statistical properties on that data, right? And so given that a lot of this is time series data, you can do many interesting things there. And then the actions are very simple. Given that you are working at the edge and you're going to be resource constrained, you want to do simple things, right? And that means send a message um, and that can trigger things downstream, trigger additional sensing, right? So you might say that if I see this, maybe I should turn on this sensor, right, so that it can do some additional observations. It could do a combination of these things. It could then try to do some approximation based on what you're seeing. So you could do some simple actions that get triggered based on these activities, right? And so again, it's not a very complex abstraction, but allows you to do interesting things with the data. This piece of work was done by Christian, but what it's trying to do is then use the function as a service kind of model to be able to create a platform for executing this using containers. And that allows us to give a more, using tools such as Lambda so that you can implement it in a more scalable manner. And we have again deployed the code so that you can use it. Um, this third piece of work then looks at the infrastructure aspect of this, right? So then the idea is that now I have got my workflow and I decide I want to run it, right? I could be doing it at the uh, at a data center if I had that as a dedicated resource, but often I need to integrate existing resources to be able to formulate and or to compose or synthesize a federated execution platform, right? That combines these different resources across the resources I have access to. And that the what type of resources I need would depend on um, what type of computation I'm triggering. So I may not know it a priori. It'll depend again on what the data tells me, right? And so what Mustafa did was to see how we can build a constraint-based model to be able to do this, right? So if I if I can describe what I want as a dynamic set of constraints, right? Saying that I need at least so much memory, I need this kind of a security environment, I need this much CPU availability or this kind of scale or this kind of physical hardware or something else, right? If I can define these set of constraints, then I can use a constraint engine to solve that constraint problem, and that will help me identify the resources that match these constraints that I have, and then I can federate them using a federation engine and be able to create an execution environment to then run my jobs, right? And given that as situation evolves, I might need different types of resources. I need to be able to have a dynamic set of constraints, right? So he uh, developed the system that could take these constraints, periodically solve the constraint using a scalable constraint engine, and then use that to identify which resources need to be federated and how to run my applications. Right? And then did some analysis to make sure that you could use this to meet the constraints you have. And there's a, a citation here that goes into a lot more detail about this model. Um, the last maybe uh, no, I have one more piece after this, but this is a different kind of work that I've been, and this is still a work in progress. This was some initial results that we had, and we are trying to uh, evolve this model. But the idea was that often I need to use all the data I can when I'm building this kind of an opportunistic system, right? When I'm doing this urgent, I need to use different types of data and find out what data is relevant to me, right? So can I use recommendation systems to be able to do that, right? And we know that recommendation systems can be very effective in being able to discover relevant information, right? And we use that, right? All these online marketing systems use that all the time. Content delivery systems use it all the time. Can we use it for scientific information, right? And turns out they can be more effective in the uh, for scientific data is because we have a better understanding of the data and the relationships between data, right? For example, um, there is a very good relation between basic data and derived data types, right? So if I'm interested in certain type of derived data, then I know that I'm going to be interested in some of the core data values that are or data sources that are out there. Another thing is that often um, these data sets are spatial in nature, and so spatial locality becomes very, very relevant here. Right? So how do we leverage those aspects and develop a recommendation system for scientific data? And so what Yubo did was to be able to create knowledge graphs along these dimensions, right? Physical locality, data models, uh, history, correlations. So a lot of different relationships created um, knowledge graphs and then created a collaborative knowledge graph that combines these. And then he used attention networks to be then graph neural nets and then attention layer to be able to use that to recommend data sets to users based on these relationships in this knowledge graph, right? And it was surprisingly effective because of the, again, nature of scientific data and the way our models use scientific data, right? So you can very effectively recommend data to the users. And again, you can run these models at the edge, right, where the data is, and start pushing data to the user saying or to the application saying that here is relevant data. You were interested in this type of data, right? Here's another sensor that's providing the same data, or this is relevant data to the application, and that makes the data discovery problem much easier. And especially in an urgent situation, you want to get all the data modalities you can to be able to make a decision, and this allows you to do that. Um, on the management side, we've been looking at autonomic techniques, and some of you might remember these from the early 2000s. Right, here's just some high-level overview. But from our perspective, what we're trying to do is to see how we can optimize the behavior of this workflow at runtime. It could be where it's running, how it's running, what resources, what type of algorithms it uses, right? And how do you make these trade-offs between cost and benefit? At this urgent situation, you have to be very careful about cost, whether it's time, whether it's energy, right? How do you balance those with the quality of service you're looking for? And that could mean multiple dimensions of adaptations. You could be changing the algorithm from precise to approximate, or the resources you use, or the amount of trade-off between data movement versus in situ computation, right? So you have a lot of different um, trade-offs you can make. Uh, and so this autonomic management system, right, that autonomic management approach allows you to do that. There are a couple of pictures here, and I'll walk through them quickly, right? So the basic idea of autonomic system is to build these uh, self-optimizing, self-healing, self-configuring systems, right? All these self-star properties using um, the human autonomic nervous system as a metaphor, right? And so the the basic idea here is that adaptive systems, biological systems, have this notion of a viability zone, right? So if your goal is to keep the organism alive, right, and you have different essential variables, blood glucose level, insulin levels, things like that, right, which sort of maintain the viability of the organism, right? And so what the adaptive biological system does is that it, whenever an external or internal event causes any of these essential variables to go outside this viability zone, it makes an adaptation or multiple adaptations to be able to get it back, right? So, for example, the glucose level goes down. You could have multiple things. You might, do regulate the insulin, right? You might also um, uh, trigger hunger in the individual, right? So there could be multiple responses that can happen simultaneously, so that essential variable goes back into the viability zone, right? And we can use the same metaphor for these adaptive systems, and that's what autonomic management does. And a lot of the systems that have been built are based on this Ashby's ultra-stable system, which is this idea of from the 1960s, right? Which has this idea of multiple closed loops, right? A local loop and an outer loop. The local loop is more responsive, using immediately coded triggers, rules that trigger something. And the outer loop is this assimilation of new knowledge. You can think about a learning loop where there's some sort of a data-driven model that's assimilating new knowledge. It could be humans there that assimilate new knowledge that then inject it again, more knowledge into the local loop, which can react very quickly, right? So this is, again, concepts that have evolved over the last couple of decades, but we're trying to borrow them out here, right? So there are two approaches that we've been using here. One is, how do we optimize within the computational model its behavior based on external triggers, right? And so this paper, and there's a sequence of papers here that try to look at this and see, okay, how do I, based on triggers coming in a more traditional uh, workflow, how can we trigger those adaptations, whether it is triggering based on how many nodes, where it's running, what type of algorithms I use, what type of data management I use. I can change all of that based on what my triggers are coming in. Right? So this was built, and this was built uh, targeting more traditional HPC systems, which are not that adaptive traditionally, right? So if you look at our traditional MPI type workflows, right, having this kind of adaptivity is hard, but a lot of our large scale models are built using these kind of programming systems and platforms, right? So the idea here was, how do I trigger some of this kind of adaptation in a more traditional HPC system? More recently, we have started a collaboration with Project Tima out of, and we're working with the team in Sicily in Messina, where we are trying to use a similar idea for cross-layer uh, management of these end-to-end workflows. And the idea here is to really uh, combine adaptations at different layers, right, and at different aspects or locations in this continuum at the global or the in-network or the edge layer, right? How do you have multiple adaptations, and how do you do this in a cross layer? For example, you evaluate different options, right? Do I change the algorithm which sends more data, or do I that reduces the amount of data, or do I send more data and optimize the network and find the network path, or energy versus right? So can I make multiple adaptations? And going back to the example in the previous slide of this viability zones, we can think about this as a keeping this application in its viability zone using multiple simultaneous adaptations, right? And so this is what the cross-layer approach here is trying to do. Looking at time, I'm going to speed up. So I'm going to switch a little bit right now and talk about uh, a platform we are building called the National Data Platform, which is trying to combine a lot of this research in a production mode, right? This is in collaboration with a number of groups, including, and it's led by the San Diego Supercomputing Center at the University of California, San Diego, right? So the idea here is, how do I create a data platform that can combine these things so that it can provide access to data and data-driven workflow in a more open and democratized way. Right? So this is really trying to create what is the core services that I can run at the edge, at the core, or at the in the network that can support this, like the services I talked about for data streaming or workflow triggering and autonomic management. Um, the basic architecture here is really one of a platform. You have a notion of a hub, right, which basically creates a entry point. It has a notion of a portal where you can come in and connect and discover and use data sets, define your workflows. But then it has this lightweight data points of presence, right? And what these data point of presence do is they can run close to a data source where you can deploy services there, right? For example, if I wanted to run my rPulsar service or staging service close to a source, to a data source, I can deploy my container there, and it can run on this platform and then be able to execute there. So it allows us to build a platform to really build these continuum workflows from a user perspective. Right? And we've been working on a bunch of different applications using this platform. Um, Key among this, and I won't go into detail here, looking at time, is a staging service which allows us to create temporary storage for data so that I can operate on it in the network or at the edge. And then the other one is a data streaming service, which is based on the rPulsar model that I talked about. And again, the idea here is to be able to support these kind of urgent and other continuum workflows, right? So how do you create the basic services that can then support this in a more production environment? And just to give you an example, right, here is one of the workflows that we are working on, and this becomes important in the use case that I'm going to talk about next, right? So what we are doing out here is, I'll talk about EarthScope. EarthScope is a environmental observatory. It has a lot of sensors that are streaming data, and one type of data that we are interested in is GPS data, and I'll tell you why. It's very important in early earthquake warning, right? And so it has about 2,000 plus GPS streams, and you're trying to use them to detect um, displacements that happen, right, and be able to see whether those are significant enough that you should be concerned that this could be start of an earthquake, right? So that's sort of the idea here. And so what we can do out here is to be able to create a data point of presence that runs close to these sensors, and then you can run your R-Pulsar programming model that can detect and react to possible changes in displacement across a window and across multiple GPS streams. You can connect it and compare it with history and be able to see whether you're seeing uh, an anomaly based on historical values. You can also use it to trigger workflows using, in this case, Open Science Grid, right? So it's really being able to deploy these services in the right places so that you can do this end-to-end workflow using this platform, right? So the based on what I just talked about, one workflow that we are working on, conceptual idea here was published in 2020, but it has been evolving since in a more practical way, right? But the idea here is how do you do using a platform like what I've described, how can I do early earthquake warning using a combination of different data sources, right? Traditionally, you use seismometers to be able to detect seismic activity and then detect earthquakes. But we've typically found um, for large earthquakes, right, there's a lot of noise, right? And the reason is very simple, right? At a large earthquake, the ground-based seismometers are also moving, and they can create errors in the data. But if you can uh, introduce GPS data along with seismic data, right, you can do two things. You can detect it, large earthquakes more accurately, and you can do them earlier because they can detect the displacements before the seismic activity actually happens at the sensitive area, right? And so if I look at the picture on the right here, right, we are trying to catch these surface P waves, which are the early warnings of the more uh, intense S waves in the core, which cause the damage, right? So if I can detect these early waves using GPS sensors in a distributed way, right, I can give enough of a warning, right? For example, to shut down the metro system or to evacuate a hospital, right? So I can do certain things by getting a little more warning there. And so we've been working on creating an in-network workflow that uses federated learning to be able to do this early detection, right? And builds on the capabilities I talked about, this idea of a autonomic runtime, the programming layer on top of it, and all built on the national data platform. There are a few other applications, and I'll go through this quickly. Here's one we worked on some time back. Right? This is from 2017. And the idea, this was more post hoc, so after the damage, you're seeing how we could have done things. Right? This is part of a hurricane damage. And the idea here was to use um, in online LiDAR measurements and compare them at the edge with a database of LiDAR images of these critical infrastructure. So scenario is something like this, right? Think about a catastrophic event like a large hurricane. In this case, we're looking at Hurricane Sandy in the New Jersey area, right? So a large hurricane, it damages, the winds can damage critical infrastructure, bridges, buildings, right? And so you need to quickly detect whether those are still safe to use or not. Think about a bridge, right? Can I make a determination whether the bridge can still be used or do I need to quarantine it? And so, and that's important because those are the routes you want to use to bring supplies in or evacuate people. And so what happens here is that you have a database of the images of these critical infrastructure in healthy mode, right? So after this event, you go back and re-image it, and you can quickly triage this at the edge, right, on a drone or on a vehicle that's doing the lidar imaging, and make sure that you can detect, is this safe, is this damaged, or I don't know, right? And for those that are damaged, I can quickly shut them down. Those that are safe, I can use them. And when I don't know, then I can do additional analysis, right? But this allows us to react very, very quickly, right? And so this was just a proof of concept that we did after the fact using data from this hurricane to be able to show that can you really run these kind of workflows and are they useful? And here's some data. I'm going to skip this, but this is some experiments we did on the trade-offs for an autonomic management system under different conditions. Um, I'll start concluding now and talk about what we are doing right now, and that is to try to address a problem that we have in Salt Lake City, and that is air quality. And one source of bad air quality comes from uh, fires, right? And we're seeing a growth in the number of fires, especially on the U.S. West Coast here, or even in Canada, right? And the smoke from there can cause a lot of health impacts. And because it's a valley, right, the the air quality can go from very good to very bad in tens of minutes, right? And so you have to react quickly. So like, for example, you want to open up shelters, make sure that the high, air filters are working, try to get elderly people off or sensitive people off the road, right? Issue warnings, close down schools, a lot of things you can do if you get a 10-minute or 20-minute warning before the air quality is going to get really bad, right? So how can you use weather data, uh, wind data, fire intensity data, use that in a combination to be able to do warnings. And usually you can do this over distances of hundreds of miles if you can detect it early enough and use it to feed your air quality models. And so that's the type of application we have been working on right now, using some of the sensors that have been deployed in California, as well as along the data path uh, and then at Salt Lake City here as well. And this is just extrapolating and saying that this is while we are working on one use case, you can think about many such cases where there is a pattern. There's a pattern of workflow that we can try to create, and then the question is how do you enable these workflows for a variety of situations, right? And how do we combine data, computation, modeling, actuation, and leverage the continuum to do that. Okay. I'm going to skip that. This is talking a little bit about a national government effort that's going on to actually support this kind of urgent workflows at the national level. I can come back to it if there are questions later on. Uh, so there are a lot of challenges here, right? And I talked about some of them, but I wanted to just create a larger list out here, right? I talked about driving computations to data. I think that's something that has to evolve. We have looked at some things, but I think especially injecting uncertainty that exists in data quality, data availability, resource availability. How do you inject uncertainty and make decisions on uncertainty, and what are the right abstractions to reason about uncertainty in this environment, right? And that's really hard because you know I, I know how to reason about computations and data when I know what the data is, but when things are, when you don't know and you want to be able to create computations that somehow account for the uncertainty that you're seeing in the execution environment as well as in the data. How do you express that? Uh, as you can expect, security, privacy, and trust becomes a huge issue here in being able to use resources, drive computations, make actuation, understand the provenance of the data that you're getting. Um, are there approximation models that you can build in that can use things like swarm intelligence to be able to make decisions in a distributed environment? How do you manage the workflows? How do you do a trade-off between quality and cost, right? And cost could be time, it could be energy, it could be anything that's critical at that time. So how do you make the cost, right? Sometimes yes, you have a lot of data, but adding data, the benefit of adding more data may not be worthwhile, right? Sometimes I want to make a good enough decision, right? So while I can increase the precision, right, it's not buying me anything because all I'm trying to detect is option A better than option B, and to do that, I don't need a very accurate computation. So there's a lot of uh, cost benefit analysis that has to go on, and that's where market models and utility models can help, right? And it's really sometimes you're making a decision is that given this time, what is the best computation I can do, rather than saying, what do I need to do this computation, right? So you're trying to optimize differently here, and what is the type of computational models, execution models that can support that. So there are a whole bunch of research questions here that are still, it's a rich research space. But I also want to emphasize the translational research. This is something that I've been working on with David Abramson, who used to be at the University of Queensland for some time. And the idea here is that it's not enough to do, while fundamental research in computer science, computational science is important, it's not sufficient, right? You also need to translate this in a sort of a closed loop manner where you can get feedback from the translation to further optimize your foundational research, right? So how do we build in the models for translational innovation? And I think uh, has to be part of our research agenda to be able to really impact an area like this quickly, right? We see the number, the frequency, the intensity of these events increasing. We know that computing data, the continuum, can help us. How do we make sure we can have that impact quickly? And I think we need to think consciously about the translational aspects as well. Um, so let me stop here and open it up for questions. So thank you. One thing I want to say before I stop, and going back to the Responsible AI Initiative, we have a bunch of different programs we have launched here, and there's a QR code here. But one is a distributed visitors program where we want to host people working on these kind of challenges. Come here, spend anytime you have a week, a month, a year with us embedded, so that we can collaborate on research. And we also have a postdoctoral program, right, where we are open to postdocs and you can find more information online. Let me stop here and open it up for questions. Thank you for your attention. Back to you, Rosa, Francis.
Thank you, Manish. I mean, it was a very interesting talk. I mean, I think that it went a lot on the platform and on the efficiency of how can we use the continuum, this novel infrastructure. We have a couple of questions. The first one, it's for you, which is the difference between an application and a workflow? So I think it's an interesting question.
I agree, and I haven't thought about it, but um, I think an workflow is one aspect of an application, right? So you can think of an application composed of multiple workflows, and you can even think of them in a recursive way, right? Because there's a workflow that is used to collect data. There may be another workflow that's used to then process that data, and the application has a combination of workflow that can change in space and time, right? So you can think about an application using different combinations of workflow as it evolves to have its objective. If my objective is to optimize the fuel consumption of an airplane, right? I can think about multiple workflows that come together to achieve that goal. Or if my goal is to um, issue an early earthquake warning, I can think about different workflows, right? If, for example, if I have seismic data coming in, right, then I can have a workflow that acquires seismic data, cleans it up, calibrates it, and feeds it into my model, right? Now, if I have GPS as well, my workflow changes because now I introduce GPS data, right? If my data is noisy, that might add another day for cleaning up the data. If there's missing data, I might use a interpolation or synthetic data generator workflow, right? So you can think about multiple workflows that can come together to achieve my goal. I don't know if that's helping. Uh, Actually, I think maybe Rosa would be able to answer this question much better than I can.
Yeah, I think everybody can have a different answer. So sometimes I talk more than say application workflows in the sense of, for me, workflow is an application that has some differentiated parts, no? For example, a typical HPC application, like an MPI application, will not have like these different stages that can be of different nature, no? For me, workflow implies that there is some kind of heterogeneity, no? That there are differences on the components, no? But it's true that after all, if we are working on the application area, those are applications, no? Are implemented as workflows, but are applications. So yeah, it's
Right.
We can talk about it the
Yeah,
whole night.
no, it's a good question. I hadn't thought about it, but very good question.
Yeah, then I had a question myself. Thanks a lot. Well, of course, thanks a lot for the presentation. From the use cases that you have been presenting, I've seen a lot the use of the edge sensors and so on. But in these use cases, is there use of HPC, like for simulating the impact of the earthquake or things like this, or is not considered?
No, we do have HPC more traditional workflows that do it. For example, a lot of well, definitely for the air quality models, the wind models, the cloud models, all of them are very large scale HPC models. They run on thousands of cores, right? So we try to run them. In the seismic also, we have a mixture. We have the online, which is more of a data-driven model, right? But a lot of the calibration is done, and we run them offline using these traditional HPC type models there as well, the seismic codes. And so all of them have a combination of more traditional HPC type of simulations that get triggered, right, by certain events, right? Most recently, the air quality is the one where we have an ensemble of models that run the moment you detect something, right? And so the question is, you have a gradation of the accuracy of the model, right? So you can do something quickly and then refine your decisions based on more data coming in from the models.
Okay. Then there's another question on the chat regarding the energy consumption and how to measure it. And especially when we are dealing with environments like the cloud, where things are virtualized and you don't have access to the physical devices.
Right.
That's it. How can we deal with energy measurements in this kind of environments? And personally, with that, especially if it's not on our control, if it's on some company premises, then how can we optimize the energy consumption here?
Yeah, that's a good question, and I don't have a good answer there, right? I think we sort of have built on the assumption that we have that control, but if I'm using a commercial cloud, then I don't, right? Now, edge devices, you have a little more control on the platform where you can make these trade-offs between local computation, accuracy of data, and the resolution of data and data transport, right? Those are simple. You can create models and do those optimizations. But going back to your question on the cloud type platform, especially if you're using a commercial third-party cloud, right, then you really have little knobs, right? And I don't have a better answer in terms of how do you actually get that and estimate that data, right? You could have simple estimations that you can build off, but you can never validate that you're actually having an impact.
Okay, great. I have another, I guess that we have time for a couple of more questions. One of them, you spoke a lot about the platform efficiency of how to move computation towards data, how to aggregate the resources that make the platform, and the quality of service, with the quality of service, how we can drive this, the usage of the resources. But regarding the programming of the applications, I mean, right now we have this kind of virtualized environments where we are putting all the containers,
right,
with all the logic and all the software. Does it make it, I mean, as from my point of view, it makes everything more difficult to use the continuum? Should we ask the programmers to do something about it, or how we can approach that to simplify the programming of applications on the continuum?
So I sort of look at it more hierarchical, right? You have different pieces, right? You have a large scale simulation that can model certain phenomena that's interesting to you. You have edge analytics, right? And then we are looking at how do I orchestrate across them in a data-driven way, right? So we are leveraging existing components in the native implementation, whether it's MPI, whether it is using, Python or whatever or containers or FAS, right? Whatever existing models exist, how do you orchestrate on top of it, which can then trigger these computations at the time, right? So that's sort of the way we're separating that. But I agree with you, right? If you're trying to simulate or code the entire workflow end to end, right? Then it can get very complex very quickly, especially because you have contingencies, right, that you have to code in because you don't know what the situation is. That I want to do X, but if I don't have resources, I want to do Y. And if the resource availability change, I want to do something else, right? So you have a lot of possible scenarios, and using traditional approaches, defining what to do there becomes really hard. So you need to have these two layers which can separate this orchestration separately from the computation that is being done using more traditional programming systems. I don't know if I'm answering a question, but that's sort of how we have viewed it, right? We've been looking at it more on expressing these uncertainties at a high level that then orchestrate existing programming systems underneath it.
Okay. Thank you. I think that we're almost on time, and there are no more questions. So once again, Manish, thank you very much for the presentation. It was really interesting, and for the audience, we hope to meet you on the next webinar.
And with this, we are closing this year. Thanks again, Manish, for
Thank you, and
talk.
happy holidays and New
Exactly.
Year. See
Happy
you so much soon.
holidays. And we will announce the next webinar shortly.
Thank you. Bye.
Thank you.
Thank you.